Hello everyone. Before the lecture begins today, I have two announcements. The first is about the lecture itself. It is not a PowerPoint presentation that has a lot of pictures in it. It has diagrams and graphs that you actually have to reproduce during the lecture so that they'll be part of your notes so that you understand what's going on. So you need to take notes in some notebook today. It doesn't matter whether it's electronic, separate notebook, or of course you can simply use the integrated notebook along with your lab manual, that carbon copy bit in the back. The second announcement is about safety. In this experiment, you have to insert a thermometer into a thermometer adapter, and if that glass thermometer breaks, you really risk injuring yourself. There's two techniques that you can use to do this safely. Now, I'm at home, so I don't have access to either one of these things, so for the demonstration, here's my thermometer. This is the thermometer bulb, and this is the part you have to insert into the thermometer adapter, which is here. You can see the thermometer adapter has a hole in it. So friction is your enemy in this process. You don't want to just jam the thermometer into the hole. You want to reduce the friction by rolling it back and forth. And that will reduce the friction and help you to insert one into the other. The other bit is that you don't want to hold the thermometer from way back here and push. If the thermometer then breaks, that's when you really risk injuring yourself. You want to choke way up on the thermometer, rock back and forth, roll back and forth, and it should insert with ease, and you'll be safe. Welcome everybody to Chemistry 202 Lab, lecture on distillation. Distillation is an important technique in chemistry because it involves the separation of two materials. You might also call it simply the purification of a material. Separations and purifications are an ongoing theme in all three introductory chemistry courses that you take here at Emory. The first separation technique we ran into in Chem 150 lab was recrystallization. That is, alum crystallized out of solution. Alum was purified from a mixture based on solubility. Purification based on solubility, crystallization. Earlier this semester, we looked at chromatography, and this is a separation or purification of materials based on molecular polarity. Separations are extremely important in chemistry for a variety of reasons, but one of them is that pure materials are typically more valuable than impure materials. If you live in a nation without fresh water and you have to get water from the sea, you've got to separate the salt from the water before you can drink that water. As a matter of fact, until recently, this was done by distillation. Chemists have subsequently cracked the reverse osmosis code, and so now that's how we make fresh water. This technique has a long history. Written records describing distillation go back more than 2,300 years. I also want to point out that this is also a very modern technique. This photograph is of an oil refinery, and each of those towers you see in this photograph are actually fractionating columns for a distillation unit. So today in lab, if you're doing fractional distillation, your apparatus will have about a 12-inch distillation column. These are more like 12-story tall distillation columns. All petroleum products and a lot of products need to undergo distillation for purification. This course, 202 Lab, is a great time to study distillation because it relies on two very important theories and models that you've learned in Chemistry 202 lecture portion. The first is kinetic molecular theory. That is, molecules are always in motion, and when you add energy to them, the motion increases, and the temperature is a measure of the average kinetic energy of a molecule. This we use to describe phase changes. So that's where this lecture is going to start. The second theory that we use widely for describing distillation is equilibrium, and that's also been a very important part of your lecture component. So now let's look at a liquid and describe it with kinetic molecular theory. The purpose of this lecture is to teach you how to predict and describe the results of distillation. If you start with a mixture, when it distills, what will you have in the distillate? So we're going to start by describing how a liquid behaves according to kinetic molecular theory. So here is the liquid. So this represents molecules of liquid. But these molecules have kinetic energy. And because this kinetic energy is an average across all molecules, some of them have more energy and they can escape the surface of the liquid. In order to do that, they have to push back on the atmosphere. And that's why we refer to the molecules in the gas phase as representing the vapor pressure of the liquid. As we begin to heat this liquid, the molecules increase in kinetic energy, as indicated by their increase in temperature. This increasing motion in kinetic energy will result in more of these liquid molecules showing up in the vapor phase. A measure of this is increase in vapor pressure. As temperature increases, so does vapor pressure. Eventually, the vapor pressure increases to the point where it equals atmospheric pressure. And at this point, the liquid can simply turn into a gas, and the phenomenon we call boiling occurs. Now, everyone has seen boiling, but I want to spend just a second on it to clear up some very common misconception. So imagine you're watching a glass container of water boil on the stove, and you see those bubbles. A very common misconception is that those bubbles are air, and they are indeed not. Those bubbles are the gas phase of the liquid. Bubbles of the gas formed from the liquid rise out of the liquid at its boiling point. Distillation is a separations technique, so we've got to add another component in here. Let's add B in here. Keep the heat on so that the system is still boiling. And if this represents when it has reached equilibrium, we can see something about B, and that is it has a much lower vapor pressure. I say that because there is fewer molecules of B in the gas phase than there are molecules of A. So lower vapor pressure also means that B has a higher boiling point. The second important point here is that for an ideal solution, which this diagram is meant to represent, and we'll talk more about what makes a solution ideal, that when you have a mixture, the vapor above the liquid will always be more enriched in the low boiling component. So there is more molecules of A in the vapor than there are molecules of B. A is the lower boiling component, B is the higher boiling component. Now I hope at this point you're also wondering what in the world this has to do with distillation. This model, this scientific model, is a proxy for what actually occurs during distillation. So what we have in distillation is a boiling flask that contains the liquid, and we're heating that flask. We heat it to boiling and establish the same kind of liquid-gas equilibrium, phase equilibrium. Now the distillation apparatus also has a place for that vapor to travel. The vapor travels into a condenser. Condenser is a glass tube with another jacket around it through which water flows. We put a thermometer in this system also because knowing the temperature is the only insight we can really get into the nature of what is distilling. And that's ultimately what we want to know, what the distillate is. As I said, this model is the best proxy we have to describe distillation. This area, the vapor phase, in our model is meant to represent this very real area. The composition of the vapor above the liquid here will be the same as the composition of the vapor here. Or at least our model gives us the best approximation of the composition of the vapor here. This vapor, however, will cool and condense to a liquid, and this is the liquid that we collect. I'm going to be collecting today in a small graduated cylinder. And so the composition of this vapor is, let's see, there's 5 molecules total, that's 4 of A and 1 of B, is 80% pure A. So that's the composition of this vapor, that's the composition of this vapor, and that's our best proxy for the composition of the liquid that's dripping out of the distillation. So if you distill a mixture that's 50% A, this model shows us that we will get a distillate that is 80% pure A. I again want to emphasize that in an ideal solution, the distillate is always going to be enriched in the low boiling component. We've gone from 50% to 80% pure. So this is our model for how liquid-vapor equilibrium relates to distillation. Now we want to be able to figure out exactly what, given a mixture that we're trying to purify, will result when you do a distillation. In order to do this, we're going to investigate phase diagrams. A phase diagram along the x-axis is the mixture we're talking about. On the left side, be pure component A. On the right side, be where there is no component A. And then that same axis also describes component B. 0% B over to 100% B. So this x-axis describes every mixture of these two components possible. So here is going to be 50% A. The y-axis is temperature. So we know the boiling point of pure A. And this would indicate the boiling point of pure B. A was the low boiling material, and B was the high boiling material. When two liquids form an ideal solution, Raoult's law governs them and says that the boiling point of the mixture of A and B must be somewhere between the boiling point of pure A and pure B. Furthermore, it's not a linear relationship. The numbers just don't simply go directly up, but rather there's an exponential term in there. So that gives a curve. And so the relationship will look something like that. This line indicates the boiling point of every mixture of the ideal solution. This boiling point line is also called the liquid line, because everything below it is the liquid phase. So a 50% solution of A and B will have this boiling point. So we can find the boiling point of any mixture of A and B. This is critical because we want to know what is going to happen when we boil this solution. What is the vapor in contact with that liquid? Because that is the vapor that's going to distill over. And that's what we're trying to find, the composition of that vapor. This is found by another line, also governed by a Raoult's law. And it's going to look something like this. This is going to be the vapor line. The bottom line indicates boiling point. The top line indicates the composition of the vapor in equilibrium with that liquid that is boiling. It is that vapor that's going to distill. It's that vapor's composition that will determine what we get in a distillate. So what is the composition of the vapor at the boiling point? That's found at this intersection of the boiling point and the vapor line. And that's about 80% A. There's something very important to look at here, and that is when 50% pure A distills, it is enriched in the low boiling substance. So the percentage of low boiling material enriches during a distillation. It's also important to note that even though B is higher boiling, some of it boils, co-distills with A because it has a vapor pressure. This phase diagram is supposed to mimic what this sort of cartoon told us, that a 50-50 mixture gives an 80% pure distillate enriched in A. At this point, I would like everyone to open their lab manual to page 74 and use the phase diagram that is drawn there to answer this question. This is important because you need to be able to figure out the composition of a distillate, as I just did, using a phase diagram when you're given a mixture to distill. So turn to page 74. As you work this problem, you're going to be better off if you draw on the graph. Don't just write an answer down to question 1 or to question 2. Point to the graph and show us exactly how you did it, with circles and lines and arrows, just as I did. Let everyone see how you're working the problem. So at this point, I'm going to pause and get everybody caught up on how to use a phase diagram to determine the results of a distillation. All right, now I'm going to check your understanding by working the solution. The first question is, what is the boiling point of the low boiling liquid? And first of all, you have to figure out what the low boiling liquid is. It's either going to be A or it's going to be B. Well, B has a high boiling point and A has the lower boiling point. So question number 1, the boiling point is 80 degrees C. The second question is, what is the boiling point of a mixture containing 25% A? So you've got to look at this x-axis and locate 25% A. Remember that this is 100% A. This one's not labeled, but this would be 0% A. So we're looking in this space of the graph, 10, 25. There's 25% A. And then I'm going to put a straight edge right on the screen and draw a line up to that. Now that I know the intersection, okay, my straight edge was messing with the screen. Find the intersection of this is 94 degrees. So a mixture that is 25% pure will have a boiling point of 94 degrees. Now the third question is, what is the composition of the vapor at 94 degrees? Another way of saying that is, what is going to distill off? Well, the composition of the vapor line gives us that information. And so let's find out where 94 intersects that line. The intersection is here. So this is the composition of the vapor at 94. To actually read the composition, you need to head down to the x-axis, and that's 50%, 60%. So that would be 65% A. And that would be the answer to question number 3. So if 25% A boils, it will give a distillate that's enriched to the point of 65%. Again, the distillate's always going to be enriched when compared with the liquid in that low boiling component. In this experiment, you're going to compare simple and fractional distillation. So I want to give you just a quick look at that. We know that in simple distillation, if you distill 25% A, it will yield a distillate of 65% pure A. In fractional distillation, the one thing we can guarantee that is if you distill 25% pure A, you're going to fractionally distill a mixture that is greater than 65% pure A. The reason that I'm not going to be any more committal than that is that the quality of fractional distillation, the separation you get, depends on two things. One, the kind of column you use. That is, you're using a 12-inch column, and I showed you a photograph of a 12-story column. There are different columns that give different results. The second is that technique is also important. Exactly how this happens can be viewed sort of schematically. Here's our fractionating column, and the fractionating column you have is filled with a stainless steel sponge. At the bottom is a boiling flask. We know the composition of the boiling flask to be 25% A. As this boils, that vapor will travel up into the column. We know that the composition of the vapor is going to be 65% pure A. What happens in the column, however, is that some of that 65% pure material condenses. It's a little cooler up there, and it begins to form droplets that are also 65% pure. These droplets are heavy, they start to roll back down, but what do they meet along the way? Hot vapors. So now instead of having 25% pure material boiling, the liquid that boils is 65% pure, which will give a much higher ratio of the low boiling component. This is what goes on to be cooled and condensed in the condenser. So essentially, we're redistilling something that's already been distilled. People also make the analogy of somehow chaining two distillations onto one another. You distill once and then you distill again. But all that happens on the surface that's in that column. So it's hard to pin down exactly what we get from a fractional distillation. We just know it's going to be better separation than from a simple distillation. So now that you know how to use a phase diagram, I want to talk about where they come from. First of all, they can come from simply doing experiments. You make a 50% solution, you measure its boiling point, and plot that on your graph. Then you extract a little bit of this vapor and find out what its composition is. And you plot that on your graph. And then you get 10 of your best friends together, and each one of them makes up a different solution. And the boiling point for each solution is plotted. And they'll make a nice smooth curve. there is the liquid or boiling point line. Each one of the compositions for these is also measured and plotted, and that's how you find the vapor line. So this is a lot of work, to tell you the truth, but it's been done for lots and lots of mixtures. And this is how an experimental result can give you a phase diagram. Now, I've referred to ideal solutions and Raoult's law. This is not a course in sort of these physical laws, but just like the ideal gas law exists that describes gases behaving ideally, Raoult's law will describe how two solutions exist. So these phase diagrams can also be derived from theory. So when two liquids mix to form an ideal solution, the experimental results of the phase diagram will look exactly as is predicted by theory. So even though we call it a law, Raoult's law, not all solutions choose or have the ability to obey that. Some misbehave. This is really no different than the ideal gas law. PV equals nRT describes the behavior of a gas, and we will call that gas behaving as an ideal gas. If it behaves in some other way, it's behaving in a non-ideal fashion. And indeed, solutions can also behave in a non-ideal fashion. That means that what you predict from theory will not match the experimental results you see. Just like gases can behave in a non-ideal manner, solutions behave in a non-ideal manner too. So I want to discuss this non-ideal behavior now, mainly in comparing it to ideal behavior. So I'm going to make a quick phase diagram here that represents ideal behavior, a low boiling component, a high boiling component. The boiling point of the mixture will look like this. In a non-ideal solution, that is a solution that doesn't obey Raoult's law, the boiling point of the mixtures do not have to be between the boiling point of the two solutions. So somewhere along the way, there could be a point that has a lower boiling. And that would look like this, and maybe like that on the other side. So here we have a mixture. With a boiling point that's lower than either of the pure components. The vapor phase follows for non-ideal and ideal, like you would expect. Now, see what happens here. If I have a mixture that boils, it will give me a boiling point here, and distill to give this mixture. So liquid and vapor, which is the distillate. And this is the same as ideal behavior. The vapor is more enriched in the low boiling component than the liquid is. But look what happens on this side. We boil this liquid. It will boil at this temperature. And it's actually more enriched, the vapor is actually more enriched in the high boiling material. It's non-ideal behavior. So in non-ideal solutions, you don't necessarily have to always get more of the low boiling component. There's another feature of this, and that is this point along the way. If you'll notice, it has a constant boiling point. If you make a mixture that has this composition, it will boil with one temperature from beginning to end. The first drop will have the same composition as the mixture itself, and that will not change all the way to the last drop. This particular mixture has a name called an azeotrope. I guess its translation is it boils without moving or without changing. Because just like a pure liquid, it will boil with the same temperature and the same composition from beginning to end. Non-ideal solutions are pretty common, and as a matter of fact, water and ethanol form a non-ideal solution. In this particular case, the mixture, the azeotrope, for water and ethanol is at 95% ethanol. So this particular diagram isn't accurate. That mixture would be way over to the left. The boiling point of the mixture is just a fraction of a degree below the boiling point of ethanol, but it's still lower. So that means if you make a 95% mixture of ethanol, it will distill from beginning to end with the same temperature. It also means that if distilling ethanol, the very highest amount of ethanol that can be in that mixture is 95%. Percent is one way to measure ethanol. In the beverage world, proof is very common. Proof is simply 2 times the percent. Therefore, if you go to the Toco Giant, you'll find the strongest grain alcohol they sell is 190 proof. The last thing that I want to emphasize about distillation is that it is a process. Through this talk, I've used a phase diagram to describe what happens when a mixture boils, what kind of composition the distillate will be. In this instance, you can see the low boiling material is being removed from the pot at a high rate. That means that the pot itself will have a changing composition. In other words, this line will keep moving. A while later, the pot composition will be here. After a time, again, the pot composition will change. So everything I've said about distillation is simply at a moment in time. In order to piece this together, what a distillation might look like, you have to realize that you could kind of construct a movie with each one of these pot compositions being a frame, and when you run the movie frame after frame, you see distillation as a process. This is better described not by phase diagrams here, but by a distillation curve. And you're going to prepare that from the data you collect in lab today. This is a plot of temperature of the distillation versus volume of the distillate. A distillation of two materials will start at a low temperature. It'll rise up and then eventually plateau out. You can simply collect data in a volume and temperature table and then plot it later. You're going to compare the distillation curve for simple and fractional distillation. You'll be doing one distillation, your neighbors will collect the data for the other. You could collect this data at any interval, but I think 2 mils is reasonable. Less would be tedious, more you wouldn't get the resolution to make a nice graph. But this is the result of the composition of the pot constantly losing low boiling material. It becomes higher and higher boiling along the way. You're collecting 2 sets of data during this, and that is noting the volume and temperature, but also you're cutting fractions of approximately 10 ml. By the boiling point, you can see that this fraction has more ethanol, and I know that because it has a lower boiling point. This fraction, where the boiling point is getting close to water, has less ethanol. In order to calculate a yield from your reaction, that is, sugar reacts to give ethanol, you've got to know how much is in each one of these fractions. And that's not going to be hard to do because you know the volume of the fraction. You know the mass of the fraction because you weighed the graduated cylinder before and after. And this gives you density. And then from the alcohol table of densities, you can turn this into a purity. So for example, if you have 9 grams of distillate, that's 70% pure, you can calculate grams of ethanol. It'd be about 6.3 grams of ethanol in that fraction. In order to calculate the total yield, you need to do this for each fraction and then sum them up. Once all of the ethanol is distilled away, you can stop distillation, drop the heat source, and let things cool and clean up. How do you know when the ethanol is gone? That's going to be indicated by this boiling point. So when you see the boiling point of water, you know you can stop distillation. We've noticed that even with calibrated thermometers, sometimes you get a plateau of temperature that is not exactly at the boiling point of water. It's a degree off. We think that this is just random error in the measurement of the thermometer. So if you don't want to rely on the boiling point of water that your thermometer gives, you can know that when this line becomes flat, you are simply distilling water, and that you can end the distillation. From this lecture, I wanted you to be able to learn how to use a phase diagram to describe a distillation. When you start with one mixture, what will distill over? You should learn that with ideal solutions, what distills over will always be enriched in the low boiling component. But if the high boiling component has a significant vapor pressure, some of it can also distill over. This is not the case, for instance, for desalination, when you can boil off pure water and the salt has essentially a vapor pressure of 0 and none of it will distill. What I regret is that this talk didn't have time to talk about fermentation. A couple of 3 weeks ago, you put sugar with water, some nutrients, and yeast, and the yeast actually did the work of turning sugar into alcohol. That's the chemical reaction we're talking about, and we really haven't had a chance to discuss it. I know that your biology classes will talk a lot about it, and if you stick with chemistry and biochemistry, you'll learn a lot about fermentation then. So I'm afraid I have to gloss over it in favor of just talking about how we purify ethanol away from water. You've set up your fermentation. Now it's time to distill and purify your alcohol in the lab. Good luck.